This video will cover the destructive test of an unrestrained light frame wood structure model. This test is the first part of a comparative study that will investigate the behavior of a light frame wood structure model with and without the roof harness retrofit system. At 10 feet by 10 feet plan by 3 feet in eave height, the structure is a 1/3 scale model of a typical 10 meter by 10 meter by 3 meter in eave height gable roof house. The model roof has been specifically designed to emulate the behavior of the corresponding full-scale structure under similar wind loading conditions. This is achieved by reducing the cross-section of the roof truss and sheathing components while selecting a smaller nail size for the toenail connections. For this test, withdrawal of the toenail roof-to-wall connections is isolated as the failure mode, as it is typically the most catastrophic and increasingly common form of wind-induced damage to light frame wood structures. This test specifically assesses the displacement behavior, failure mechanism, and failure wind speed of the unretrofitted structure. The test specimen is placed such that the ridge of the roof is perpendicular to the direction of wind flow. Visible here are the 4 trusses and corresponding roof-to-wall connections along the windward face of the model. As fan speed increases and suction is induced over the roof, displacement will occur at these locations. Wind speed is measured by the upstream Cobra probe mounted at eave height. Pictured here is the outdoor testing setup at the Windy facility. The 3-dimensional linear contraction, observed in front of the test specimen, is used to increase the wind speed produced by the bank of 60 fans just inside the wind tunnel. The garage doors on either side of the building are open such that wind flows through the tunnel in an open circuit configuration. One of these 2 garage doors forms the upper portion of the contraction. In the following video, evidence of 3 distinct stages of failure will be visible. In order, these stages are initial displacement of the roof-to-wall connections indicating net uplift, initial full withdrawal of a single roof-to-wall connection, and lastly, full withdrawal of all roof-to-wall connections. Initial displacement of the windward roof-to-wall connections can be classified as a serviceability failure, allowing for the formation of a gap along the windward eave and allowing potential wind-driven rain to penetrate the building envelope. Full withdrawal of a single roof-to-wall connection is a structural failure, affecting the load distribution between the roof-to-wall connections and accelerating the failure process by shedding load attributed to the failed roof-to-wall connections towards adjacent roof-to-wall connections. Finally, failure culminates with all roof-to-wall connections fully withdrawn from the top plate, at which the roof is overturned about the leeward wall. In this test, however, overturning is prevented with the use of internal cabling to protect the surrounding testing environment. To summarize what we just observed, initial separation of the roof-to-wall connections occurs at an average wind velocity of approximately 34 miles per hour. Then, at an average velocity of 47 miles per hour, the first roof-to-wall connection experiences full withdrawal, and shortly thereafter, total failure of all roof-to-wall connections is observed at 54 miles per hour. It's important to note here that the relatively small difference in velocity between where one and all roof-to-wall connections fail is due to, as previously mentioned, the loss of one roof-to-wall connection overloading adjacent roof-to-wall connections, which precipitates a progressive failure. Thank you for watching the first segment of this 2-part investigation, and we hope you'll join us for the next segment, in which we will look at the performance of the same roof with the roof harness applied.